Right, hi podcasters and listeners. We're going to learn all about compound semiconductors, a key element in 5G and 5G standalone and going forward into the future to 6G. Equally over here, we've got a data center, in real life, and one on the other side as well. This is hopefully going to be a very interesting episode. I say we're going to learn lots and lots and lots about this critical industry, and equally critical not only to the UK but to South Wales, and what is a cluster for this technology in South Wales and has become a globally important section of industry. So let's go in and we'll learn a little bit more. So welcome everybody, and welcome to another Live Better Connected podcast. And today I am at the Compound Semiconductor Application Catapult. Bit of a mouthful, but this is a really fascinating technology that is really taking over South Wales and equally the whole of the UK in terms of its compound semiconductors. I'm going to learn a bit more about that. But today I've got with me Wyn Meredith and Joe Gannicliffe. So Wyn, could you just explain a bit about yourself and who you are and your role?
Yeah, sure. My name is Wyn Meredith. I'm one of the founding non-exec directors of the Catapult. My day job is looking after something called the Compound Semiconductor Centre, which is a materials research innovation entity, and I'm also chair of the South Wales Semiconductor Cluster.
Excellent. We'll learn a little bit more about the whole cluster that's happening in Wales. It's fascinating. And Joe, yourself and your role and what you do.
Hi, so I'm Joe Gannicliffe. I'm head of photonics and RF at CSA Catapult. So responsible for the engineering technology teams, delivering advanced telecoms hardware, and also providing services in terms of testing.
Excellent. And just for those who may not know, photonics, what does that all mean?
Yeah, so photonics is basically the science and technology of light. It's a term that maybe not everyone is familiar with, but actually in terms of the application space, it's related to telecoms, it can be related to displays, it can be related to all the optical things that you have on your mobile phone as well. So it's pretty broad.
Excellent. We'll come into that, and that's including things like your face recognition and things like that.
Yeah, exactly. That use photonics technologies like time-of-flight sensors.
Excellent. And we'll find that's particularly important to the mobile industry, but we'll get on to some of those questions. But I first thought, whilst we're here, we said, we're in the Compound Semiconductors Application Catapult. What is that?
Well, it's a government-funded initiative which sits between sort of industry and academia. The main activities are really around the commercialization of new technologies. In this particular instance, it's mostly focused on new applications of compound semiconductors across radio frequency technologies like telecommunications, through to photonics, sensing, and also power electronics. So it's a collection of about over 100 people, mostly engineers and scientists, who are really looking at how to commercialize new technologies in these advanced materials.
And particularly, as you say, compound semiconductors. So, the first question I have to ask is what is a compound semiconductor?
Well, a compound semiconductor is anything that's not silicon, because when we think about semiconductors, we typically think about silicon chips.
And like a silicon wafer.
And a silicon wafer and sort of microprocessors. So compound semiconductors are not new materials. They've been around really since 50s and 60s and have already enabled a lot of technology that we're pretty used to. Everything from the laser that transmits data down the fiber optic network through to enabling old technologies like CDs, DVDs.
Remember them.
Exactly, remember them. And also new technologies. So for instance, if we look at electric vehicle technologies, silicon carbide, which is a compound semiconductor, is replacing silicon in the power electronics, so you get more range, more distance, and faster charging.
I was going to say faster charging. So we're starting to see up from 7 kilowatts. I think, in my house at the moment, I saw one going up at 500 kilowatts.
Correct, that's right, yeah. So compound semiconductors, 10 to 15 applications where it's either too harsh an environment for silicon semiconductors or some functionality which silicon can't do. So for instance, you can't have a silicon microchip laser, but you have a compound semiconductor microchip laser.
So it's not one or the other, it's them working together.
Absolutely, it's a complementary technology.
Okay. And I we'll come back on to sort of compound semiconductors, but equally, this has grown up in Wales, and particularly South Wales. We're here in Newport today. Why is there a cluster in Wales? What's particularly special about the area?
Yeah, really, really good question. It's always been a historical strength, to be honest. A lot of the companies in the core industry based in South Wales in compound semiconductors have been around here a long time. So we've got companies such as IQE, which was founded in 1988, which is a supplier of compound semiconductor material solutions. We've got Microchip Technologies, which has been here really since, again, the early 80s, looking at packaging semiconductor devices. And one of our co-partners, KLA, that was actually spun out of Bristol University in 1968 to develop a manufacturing solution for semiconductor materials. So a lot of the core industry have been around a long time, and there's also been a lot of activity in terms of research activity in Swansea and Cardiff University in compound semiconductor materials. So we've always had an underlying base of activity across the supply chain, from materials through to devices and packaging devices into applications. But really over the last 10 years, I think it was back in 2015, we brought a vision to bring together all these assets together and really invest into this new unique technology to make it a critical mass in semiconductor research, manufacturing and technology.
And I mean, you were the founder of this, so I think the work you've done is tantamount. And I came here today; it's a huge data center outside. What's going on seems to be a hum of activity, but obviously you've managed to get the UK government to really back this, and it's put significant funding into this, and equally with the CSA Academia, Cardiff University, and others. So if you can tell us that journey.
Yeah, sure. I mean, there's a huge number of people that have been involved in the definition of the early phase of the cluster. Back in 2015, it was really one of the founders of IQE, one of the companies in the region, Drew Nelson, who recognised that at the European level there was a lot of effort in terms of defining the next 10 years of technology, and compound semiconductors were really a big part of that. So bringing together the academic partners, also our partners in local and national and regional government, we brought forward a vision really that was, how do we create a more expansive critical mass? And I guess the first part of that was investing in bringing our research and development infrastructure up to scratch. So over the first 5 years, the cluster between 2015 and 2020, there was an investment of about £250 million in terms of new infrastructure. And that includes a new research centre at Cardiff University, the Institute for Compound Semiconductors, a new centre for integrated semiconductors at Swansea University, and the Compound Semiconductor Applications Catapult. So looking at research and innovation across the whole supply chain. I guess the next 5 years was really defined by co-creation and industry partners working together and using that innovation and research infrastructure to create the products of the future. So between 2020 and 2025, a partnership of roughly 12 partners across academia, industry and government were involved in a project called Strength in Places, which was a UK government funded project, innovation project, on the order of about 50 million. And that's really brought us together in terms of a really cohesive community in the region. And
it's supposedly in the market now, I think up to this year, it's potentially worth £125 billion to the UK economy.
Yeah, it's not an insignificant market for compound semiconductor materials and devices. It probably represents about 20% of the total semiconductor market globally, but there's certainly some high growth areas which are very attractive. And especially when you can offer services across the whole supply chain from materials through to finished devices. So in the period I talked about from maybe 2020 to 25, we also had an investment of about 800 million in manufacturing facilities and advanced research facilities in the infrastructure of the region, which makes it the primary place for compound semiconductors globally.
And what's a testament to the work you've done and everyone around here that's been doing is we've had, I think Microsoft have looked at the UK and significant amounts, especially in the AI side of things, and NVIDIA has placed the chairman, the chief executive of NVIDIA was saying that the UK and South Wales best placed really to exploit this, and that's coming global recognition for South Wales.
Yes, I mean, the key to this is having a coordinated strategy, which isn't just about manufacturing expansion. It's also about skills and talent creation, as well as creating the culture and the ecosystem for semiconductor development, research and manufacturing. So we worked really hard. When we started, we could maybe identify only about 900 jobs in about a sort of 70-mile radius between Caldicot in the east, where Microchip are, through to Swansea University. And last year, we're up to about 2,800, and the ambition is to get to 6,000 jobs in that same area by 2030. So it's certainly something that has shown economic benefits. Our average wage in the cluster is about 3 times average manufacturing in Wales, and it's certainly a large contribution to the gross value of the Welsh economy.
Wow, and you've seen that from the very beginning, which must have been a pretty amazing journey that you're still on.
That's true. I don't think we expected when we started out on this journey to get as far as we have in the last decade. I think the ambition started as a lot smaller in terms of just bringing together the partners we had to have a more coherent voice and to try to lobby for better infrastructure and services for research in the region. But it's certainly grown into an economic driver in the region, and hence we've had a lot of attention and investment from Welsh Government and UK Government.
Yeah, definitely. And so, Joe, and to bring you back in, compound semiconductors. Can we again explain slightly again what are they? But what are their key benefits over the silicon partner?
Sure, thanks. I think in really simple terms, compound semiconductors provide benefits in terms of power, speed, and light. And that's how we've set the Catapult really, is focusing on these key technology areas like power electronics, RF and photonics. So like when you said photonics, I think it's not perhaps grasped sometimes for people who don't work in industry, but you can't produce silicon laser, but silicon can detect wavelengths, for example, up to a certain amount. So we tend to say photonics is application specific because it's wavelength specific. So the whole telecoms industry is based around lasers and detectors and photonic devices. They can operate and send light down optical fibers with very low losses. So that's one key area, and the benefit of using photonics with compound semiconductor devices like indium phosphide for edge emitting lasers, gallium arsenide for VCSELs, which are lower cost and vertical emitting lasers. In the RF space, we see a slightly different story, where a lot of the conventional RF technology that's used for current mobile networks in handsets and in base stations is based on a combination of silicon and some gallium arsenide. As we go to higher frequencies, so for example, as we go from the current deployment in 5G towards high frequency bands, K2, and then 6G in the future, that's where we will start to need...
particularly talking the upper 6 gigahertz, which is currently being deployed under 5G and 5G standalone. And then I think you're talking the millimeter wave, which has just been sold to, and the operators have gained licenses that as part of Ofcom's auction. And that's in your sort of 28 gigahertz to I think 32 gigahertz.
Exactly, yeah. So if you want to go to those higher frequencies, then you need materials like gallium nitride because they can operate at higher frequency with higher efficiencies.
And when just to start, one of the key things was, when we looked at the 2G and 3G networks, and particularly 3G, one operator was saying that roughly around, I think it was 1 or 2% of its network traffic was taking around 35% of its energy usage. And that's one of the big reasons why the 2G and 3G networks are set for switch off. I think we're nearly there with 3G and 2G by 2030. But that's where the compound semiconductors really come into their own.
Yeah, exactly. So I think energy efficiency of networks is always going to be a big grand challenge area. So one of the key draws of energy is actually the base stations, the units that are transmitting and receiving radio waves. Some of the core technologies within those are the power amplifiers. So it's the last stage of application of your radiation before it goes over the air. Yeah. And these just draw a huge amount of power, and actually they're designed in such a way that you drive them very hard and they're very efficient. You back off in terms of your power, and they're much less efficient. But the nature of the telecom signals you need to send means you need to modulate with these very complex patterns, and therefore you need to apply quite technically challenging architectures to the semiconductor chips to actually be efficient, high power efficient at this back off frequency as well. And that's where you need some, both material benefits, but also the expertise within the design and the packaging as well.
Excellent. And then it's also in heat dissipation as well. Is that correct?
Yeah. So I think these devices themselves, when you look at how efficient they're running, they're actually very good radiators. And it's probably similar story to some of the data centers. It's kind of used some of that waste heat more efficiently.
These materials like gallium nitride, they're so-called wide bandgap semiconductors. And one of their key attributes is they're very comfortable operating at elevated temperatures where silicon isn't. So that means you can tolerate much higher temperatures. They operate at higher efficiencies at higher temperatures, so you can package them in much more dense packaging formats without cooling. So you take less on mobile applications, you'll take less battery because you don't need to cool them so much. Yeah. But it's not only the RF switching speed advantages and there's power density advantages. If you look at for instance, power electronics using gallium nitride and silicon carbide is also much more efficient. So that would also come into data center type applications where you could use this power electronics to really reduce the overall power consumption of the data centers. So it's every part of the network, it's everything from base station transmission through the handset, through the data centers. You're looking at compound semiconductors being superior components, not only in the transmission, frequency agility, power consumption, but also being able to also offer some attributes in terms of extending the applications towards the edge. So a good application we're working on at the moment is Li-Fi technology, light-based Wi-Fi, I guess in simplest form.
So this is Wi-Fi coming from your light bulbs or your LEDs.
Absolutely. Typically at the moment, the applications are based with an LED transmitter, but the problem with LEDs is they can't be modulated to very high transmission rates. So if we replace the LED with a laser, then we can modulate a gigabit scale, and so very high transmission rates in terms of the full link. And if we use addressable arrays of laser, then we can get much more coverage, intelligent coverage, which is much more robust. And so taking standard laser technology and taking new telecoms applications allows us to get much more ubiquitous coverage in technologies like that.
So the lasers are much more directional for the light circuits. So you use the arrays to actually steer the beams.
That's right.
Yeah, and I mean, the way I sort of see it and the way you're talking about it is almost like we were hitting the potential barriers that were coming up, and compound semiconductors has almost broken down those barriers and allowed us to now go to these faster, more reliable, more slow, better latency technologies.
Correct. I mean, it's only a component technology, so obviously you've got to build a system around the component technology that's going to give you and amplify these advantages for the full system advantage. And obviously interoperability is always a barrier to that, and the complexity of standardization of some of these new technologies. But looking forward, there are other areas which I think compound semiconductors can enable telecoms technology. So if we look forward to massively dense picocell technology, compound semiconductors can open up new areas of spectrum like terahertz, which allow you to get even higher bandwidths, but at very, very different spectrum.
And that's a lot faster. Lower latency, much more data in that. And in a world where we are, consuming more and more data, and we've seen it Ofcom showcasing all the networks, both across fixed and wireless, that data usage is going up and up and up. And we look at IoT, Internet of Things again.
And data storage is another area. So if you look at the latest technologies for hard disk drive technology, it's called heat-assisted magnetic recording. And in that technology, there's a compound semiconductor laser on every read head drive, which is effectively heating up the magnetic pattern, so you can get much higher density storage.
And greater storage.
So it'll take you beyond sort of 40 to 50 terabit scale enterprise data.
And we've touched on a lot of the sort of the broadcast area, which is sort of this is what's making 5G standalone and potentially 6G as it comes forward possible. You mentioned earlier as well, it's not just the broadcast and the signal, it's equally on your phones. And it's things like, I think, the facial recognition. So there's some really interesting stuff going on there as well.
Yeah, so I mean, photonics is broad because it covers detection, emission, modulation. So not only the communication side of things, but display technology is based on photonics, the imaging sensors. The facial recognition is actually based on a really rather complex method of projecting a matrix onto your face and recognizing it as a unique ID instruction.
But doing it instantly.
And doing that almost instantaneously. That's a lot of complicated integrated technology required for something that we take for granted every day, that we use our mobile phones.
Yeah, and makes them secure. And equally, one of the big things is theft and things. If if it is now personalised to you and you only, it makes it a much more viable thing. And just on that security, something I was reading about. I wanted secure 5G.
Again, we're working on some areas for new components that can exploit quantum effects and the quantum effects of data transmission. So a very secure technology is called quantum key distribution, and you need very specific light sources called single photon emitters and single photon detectors to be able to implement QKD practically. Some of the only solutions for these components are using compound semiconductor materials, which you can manufacture these very, very high specification single photon emitters and detectors. So that's another area where you're not really going to be able to implement this technology at scale without scalable compound semiconductor component solutions.
So one of the key technologies there that Wayne's talking about is something like known as single photon avalanche detector. So it kind of works like
a single photon avalanche detector.
Yeah,
so I'm thinking snow coming down a mountain. So explain that a bit.
So not as bad. I think the closest thing to think about it is like a radiation counter. A Geiger counter is just ticking away because it's counting the radiation. A SPAD can do the same for photons. So it can actually detect and discriminate between individual photons being received. And that's where in the QKD link that Wayne mentioned is we can actually encode data in a quantum state onto that photon. You can send it from A to B. And we know that if it's tampered with in the middle, the system will change because of the uncertainty principle. So you can effectively send a quantum key that you know is unbreakable, or you can send it and you know that your communication chain is now secure and fixed.
So quantum computing we're talking about here, which again is another thing that is going on here. And so I know how we're in South Wales again in the UK, and this seems to be at the cutting edge.
Yeah, sure. I mean, the UK has made a huge investment into quantum technologies. We've had a quantum technologies program since 2014 in the UK, probably invested multiple billions into research and development, and then scale up some of these quantum technologies, not just computing, but quantum sensing, quantum communications. So we've been heavily involved in South Wales in terms of developing solutions in a lot of these quantum demonstrators. The quantum computing side of things is a little bit different. The fundamental qubit technology, which is the quantum memory, if you like, and quantum logic.
So your bits in computers.
Bits of computers, right? Yeah. Typically, they can be either manufactured from superconducting elements or from what's called photonic integrated circuits, which can manipulate again at the photon level. So in the photonic integrated circuit solution, certainly compound semiconductors play a role, as we said, in terms of offering solutions for emitters and detectors of single photon devices. But actually, it's more around the ancillary and the amount of data required to service the full stack of quantum computing. That's probably where there's more opportunity for scalable volume components of quantum for compound semiconductors.
So for the qubits you just mentioned, any one way to visualize it, like you said, a bit is a 1 and a 0. A quantum bit can actually be a superposition of those states within. So if you remember,
it can be either or at any one time.
Schrödinger's cat. So therefore, you can actually kind of increase the processing power just from having a single qubit compared to a conventional bit. However, the challenge at the moment is actually developing a quantum computer in real life that isn't affected by external noise factors and making it scalable as well. So I think roughly at the moment around 1,000 qubits maybe for the latest quantum computers.
And what does that mean? Just give us context.
What does a CPU have? They need to go many times further.
So it's still at the early stages, but it's moving rapidly.
I mean, yeah, it's moving rapidly, and there are quantum computers that are accessible for certain applications. And things like brute force calculations. Yeah. It's very strong.
I think that's the key to it. Certain applications. It's not a unified solution for all future computing.
We're not going to have a quantum computer in our pocket.
We're not going to have a quantum computer in our pocket, but it's certainly suitable for scaling computing capacity for very specific computing tasks, and it'll probably end up with something that is a hybrid, a quantum as a service, which is just laid over on top of cloud computing for general purpose use.
Okay. And what's going on here? We talked a lot of sort of academia, theorizing, but this is actually turning it into usable technologies and creating a sort of sovereign supply chain in the UK that we can then start selling this to the rest of the world.
Yeah. Well, we've seen a lot of activity globally in terms of investment in semiconductors. In fact, it's been unprecedented over the last 5 years. The US CHIPS Act is 50 odd billion. The European CHIPS Act, similar size of scale. And the foundation of those CHIPS Act, is to reinvigorate domestic manufacturing as we realize the importance of semiconductors in global supply chains and some of the geopolitical factors we've seen over the last 5 years of tensions between the US and China over Taiwan, obviously the Russian-Ukraine situation. And so there's a recognition that self-sufficiency or increased self-sufficiency in semiconductors is a critical national priority. So the UK government has adopted a £1 billion semiconductor strategy that has been rolling out over the last 3 years. And to date, it's kind of been focused more on innovation and understanding what we've got in the UK in terms of semiconductor activity and semiconductor supply chains. But it is now starting to recognise that there needs to be a more coherent investment strategy in scaling up our startups in semiconductors, also connecting our maybe disparate research communities so that we're getting a critical mass of semiconductor research in the UK, not just in compound, but in other areas, traditional silicon design, emerging materials, and also packaging and scale up of semiconductors.
Because there's always a supply chain for a supply chain.
Always a supply chain for a supply chain. It's a global industry, right? It's worth 800 billion roughly per annum, heading towards $1 trillion industry by 2030. And it's very difficult to reverse that globalization. But it's certainly an argument that we build our strengths that we've already got and create some critical mass in there.
And there certainly seems some competitive advantage here. Sorry, John.
Well, I was saying that, it's clear in some areas that UK will never develop the capability, and so it's not going to develop some of these massive hyperscale factories for AI, or it's not going to be creating the latest, smallest node nanometer silicon technology, but in terms of where the compound semiconductor strengths are, then there are real pockets of expertise around the UK, obviously in South Wales in terms of chip fabrication and the cluster, but in Scotland, in Southampton, there's other areas around the UK that have photonics, RF, power expertise and capabilities as well.
And we're not the largest country, so actually we're all quite close together and hopefully creating that wider national cluster. You mentioned some of the actions the UK government is taking, the AI growth zones, for instance. Big buzzword of the moment is obviously AI. How does this fit into that world?
So I think, whether you like it or not, AI is here. And it is growing, and it's really dominating the world in many ways. We've seen huge amounts of investment in the US, particularly from big tech companies in AI data centers, AI factories. So AI itself is kind of like the brain, but in order to actually enable these AI algorithms, you need a huge amount of processing power.
But we had I think we had the AI summit, and there was a huge amount of investment, both from some of those companies you mentioned into the UK as well.
Yes, I think that there's a commitment there, and a lot of that is, I suppose, about building the infrastructure and providing the scalable technology can actually implement some of those AI solutions. But when we look at the scale of this thing, it's massive. So if you look at GPT-4, we've got some interesting stats. I think that consumed or used up 25,000 NVIDIA GPUs over 90 days. So that's £100 million of operating costs to build that model. And it used 50 gigawatt hours of energy. So apparently that's equivalent to running or powering San Francisco for 3 days. So big questions about how sustainable AI is, and to the benefits equate to the costs.
Yes, it's going to be an incredible sort of market driver for compound semiconductors over the foreseeable future.
It's going to take the role here.
Build these data centers, right? And if you look at the interconnectivity, so all the data links between the servers within data centers are mostly fiber optic data links, which are powered by compound semiconductor lasers and detectors. So that's a huge market. And the upgrade cycles in terms of the speed of upgrade at the moment is moving from 400 gigabits per second to 800 to 1.6 terabits per second in terms of a single fiber optic link. And that requires a lot of technology in terms of the deployment of new solutions, photonic solutions. But also the energy efficiency is a great area where we're going to increasingly see these materials we talked about, like gallium nitride power electronics, move into server architectures to be able to really drive the energy efficient within the data center. Because the size and scale of these types of data centers means that you've got to do some pretty radical things to be able to deliver the solutions that are required.
And compound semiconductors, again, central to AI.
Yeah,
absolutely.
Exactly. So, for example, NVIDIA, which is now the most valued company in the world, is moving towards photonic solutions. So there's a group of technologies called co-packaged optics, which is effectively bringing your optical transceivers closer to your electronic switch, your ASIC, by minimizing those copper interconnects, replacing them with fiber. It's the same principle as bringing fiber to your premises. You're reducing those losses. Signal integrity improves, and therefore you can improve your energy efficiency of these systems by 3 or 4 times, maybe 10 times in the future. The key metric that I think people are working towards is picojoule per bit. So maybe today it's around 8 or 10 picojoules per bit, and people are pushing that to 2 or 3 or 4.
And a picojoule, what is that then?
That's 10 to the minus 12.
Lots of ones, lots of zeros.
It's an incredibly small amount of energy. But then when you scale it up by the number of ports, by the data rates, by the number of processes.
And when we're generating zettabytes of data per year, so that's 23 zeros in a zettabyte, I think. So, it's these incredibly small energy per bit, but you multiply it by huge numbers. It becomes eye-watering in terms of energy consumption.
And the opportunities that AI offers are astounding.
Yeah, of course. I mean, in terms of the applications, I think from many different sectors. I think areas like medical implementations, there's a lot of rooms for improvements in terms of productivity and removing human error from certain decision making.
But it's some of those, like you mentioned, like the healthcare, and they're some of the focal points of the Catapult and the centre.
Mm-hmm. Absolutely. I mean, the whole aim of the Catapult is to look where there are potential new applications for compound semiconductor devices, and it is undoubtedly AI will drive not only the hardware infrastructure solution, but also a lot of new sensing, a lot of new sensor applications that will require compound semiconductor devices. So opportunities all the way through from infrastructure into the applications that we can't even envisage.
And a lot of these things we will eventually see via an app on our phone.
Yeah, hopefully. I mean, we're looking at technologies. A good example is atomic clock technology. So atomic clocks allow you to get very precise precision in terms of distance measurement and distance determination. Having an atomic clock on a phone would effectively give you millimeter scale distance discrimination and allow you really to make a lot of advances in terms of augmentation into virtual reality. So that's another example. We probably wouldn't envisage, 5 or 6 years ago, having that sort of technology into a phone. But in the future, I think it's, as the interfaces for phones become more sophisticated, things like that will become more important.
I mean, the question I would say is, and especially in terms of 5G. I mean, we for instance, we'd like to see national policy statements on telecommunications, for instance, more interest and more policy strategy around that. But are they doing enough? Is there more that the UK government or even the Welsh government could be doing?
Well, we've got high hopes. I mean, the UK government over the summer announced an industrial strategy, and the semiconductor strategy part of that is embedded in the digital sector plan. So there's certainly a focus on investing, as I said, mostly in R&D and looking at opportunities to be able to increase the currency investment in scale-up and startups. But I think we'd like to see more tangible activities around coordinating the national community, allowing the larger companies in the UK to be able to compete globally, because as a result of a lot of the global semiconductor initiatives, there's a lot of capital investment incentives to be able to set up in places like Singapore and Korea and Japan. And so we are in a global competitive race. So we need to recognize that. And sometimes in the UK, we're not so good at recognizing that we exist in this global ecosystem. So we'd certainly like to see more activity around capital incentives, innovation capital, creating test beds to connect the semiconductor community with the advanced communications technologies community in the UK. And also looking at a more holistic view of skills development across the UK, with a focus in not only skills for chip design, but also skills in terms of manufacturing of semiconductors and semiconductor supply chain. Because there are massive overspill effects, in semiconductor manufacturing. Typically, the US CHIPS Act used a figure of for every one job you produce in semiconductors, you would catalyze 5 or 6 jobs in advanced manufacturing if you choose to leverage that capability domestically. And that's the real opportunity for the UK industrial strategy, is to harness what we've got in South Wales and really create a renaissance in high value add manufacturing across the UK electronic systems.
Yeah. So skills, policy, clusters,
infrastructure. Most important
culture.
Can-do culture.
Can-do culture. Well, we always want to can-do culture, and I think it's that's exactly what we want to see back in the UK. We've had it in the past. Let's reinvigorate it again. Look, Joe and Wyn, thank you so much. That's been a fascinating work of what's going on here, and equally what we need to see. And it looks like a huge success, and it looks as though it's got a long future to go. And I wish you all the best on that. And certainly from a mobile perspective, compound semiconductors, I've learned something today. It really is the backbone of what we're all doing. So thank you very much. And thank you to our listeners. Once again, another fantastically interesting podcast. Please do subscribe and link on that button and share as you can. And we will see you for the next podcast. Thank you.